It's the invisible force that powers pretty much everything we do, right? From the phone that's probably in your hand to every single light in your city. Today, we're going to pull back the curtain and break down what electricity actually is.
Think about it. You do it dozens of times a day. You walk into a room, you flip a switch, and boom, the room is filled with light. It feels instantaneous. It feels like magic. But have you ever really truly stopped to wonder what is happening in that split second? Well, to figure that out, we have to start at the very beginning.
So, to really get a handle on electricity, we've got to think small. No, I mean really small. Because believe it or not, this entire world-changing phenomenon, it all starts with one incredibly tiny particle.
At its absolute core, electricity is nothing more than the movement of something we call electric charge. You can think of it as a basic property of all matter, just like mass. And this charge comes in two simple flavors. You've got your positive and you've got your negative.
Now here's the one simple rule that makes everything else work. It's a lot like magnets. Charges that are the same, so two positives or two negatives, will actually push each other away. They repel. But if you have charges that are different, a positive and a negative, they do the opposite. They pull towards each other. They attract. And that simple push and pull, that's the engine for everything else.
So what's actually carrying this charge? Well, let me introduce you to the hero of our story, the electron. Every electron carries a tiny bit of negative charge. And when I say tiny, I mean it's almost impossible to imagine. It takes about 6 quintillion of them. That's a 6 with 18 zeros just to add up to 1 coulomb, which is just our standard way of measuring charge.
All right, so we've got these tiny charged particles literally everywhere, but they're not much good to us just sitting still, right? We need to get them moving. And that brings us to the next part of the puzzle, the push and the flow. You see, when we get a whole bunch of these electrons moving in the same general direction, that's what we call an electric current. This is the flow in our system. We measure this flow in amps, or just amps for short, which is basically just a count of how much charge is flowing past a certain point every single second.
But what makes them flow in the first place? Well, they need a push. The best way to think about it is like water in a hose. Water only flows when there's a difference in pressure. It goes from high pressure to low pressure. Well, electricity works the exact same way. Charge flows from a point of high electric potential to a point of low potential.
In this push, this electrical pressure has a name you definitely know, voltage. Its official scientific name is potential difference, but yeah, we all just call it voltage. It's the energy that gets those electrons up and moving. It's simple. No voltage, no push. No push, no current. Okay, so we've got our push and we've got our flow, but it's not like the electrons get a wide open superhighway to cruise down. Nope, there's always something getting in the way, a kind of electrical friction. So, it's time to meet our third key player, the resistance. Resistance is exactly what it sounds like. It's a property that resists or opposes the flow of that current. Just like friction tries to slow down a sliding box, resistance tries to slow down the flow of electrons. And every material, even an amazing conductor like copper, has at least a little bit of resistance. We measure it in a unit called ohms. So here's where it all comes together. This is the crucial relationship. These three concepts are always linked. A push, which is our voltage, is what creates a flow, which is our current. And that flow is always limited or held back by a kind of friction, which is our resistance. Push, flow, friction. That's the whole story right there.
And this whole relationship is summed up perfectly in one of the most famous and useful equations in all of physics, Ohm's law. V equals I times R. It just says that the push, the voltage, is equal to the flow, the current, multiplied by the friction, the resistance. This little formula is the foundation for basically all modern electronics.
So what actually determines how much resistance a wire has? Well, it mainly comes down to three things. First, how long is it? A longer wire is a longer journey for the electrons, so more resistance. Makes sense. Second, how thick is it? A thicker wire is like a wider highway. It's easier for traffic to get through, so there's less resistance. And finally, the most important factor of all is what the wire is actually made of.
And the difference between materials is, well, it's staggering. Take a look at this. A good insulator, like rubber, has a resistivity around 10 to the power of 14. But a good conductor, like copper, is down around 10 to the power of -8. The gap between those two numbers is just astronomical. And that massive gap is precisely why we use copper for the inside of a wire and rubber for the outside.
So, we have our key ingredients. Now the question is, how do we arrange them?
This leads to a fundamental choice in how we build things. Do we give the electricity just one single path to follow, or do we give it many? This is all about series versus parallel circuits.
First up, series. The best example? Those old-fashioned, cheap holiday lights. You know the ones I'm talking about. Everything is connected in one single, continuous loop. The electricity has only one road it can take. And that's its biggest weakness, right? Because if one of those little bulbs burns out, the entire path is broken, and the whole string just goes dark. So frustrating.
Now, the much more useful and common way to do things is a parallel circuit. In this setup, every device gets its own separate branch, its own personal path back to the power source. So if one light bulb burns out, who cares? The others stay on because their paths are still complete. This is exactly how your house is wired. It's why your TV doesn't turn off when your toaster breaks.
Okay, let's bring all this theory back home. It's time to connect this to our daily lives and talk about the real-world results of all those moving electrons. Let's talk about power, heat, and you.
Remember our old friend resistance, that electrical friction? Well, what happens when you rub your hands together? They get warm. It's the same idea here. As electrons struggle to move through a material with resistance, those endless tiny collisions generate heat. Sometimes that's what we want, like in a toaster or a hairdryer. Other times, it's a huge problem we have to solve, like keeping your computer from overheating.
So how do we measure how quickly a device uses up electrical energy? That's what we call electric power, and we measure it in watts. This is why a 100-watt light bulb is brighter than a 60-watt bulb. It's simply consuming energy at a faster rate. More watts means more energy used every second.
But here's a little secret. When you get your electricity bill, your utility company isn't actually charging you for power. They're charging you for energy. Power is the rate you use it, but energy is the total amount you've used over time. And the unit you see on your bill for that total amount is the kilowatt hour. So what on earth is a kilowatt hour? It's simple, really. It's the total energy you'd use if you ran a 1,000-watt appliance, like a big microwave, for 1 full hour. And that single unit of electricity you pay for is equal to a whopping 3.6 million joules of energy. Kind of puts your bill in a new perspective, doesn't it?
So all of this brings us to one final thought. Now that you understand the push, the flow, and the power, just take a second. Look around you right now. Based on everything we've talked about, what in your home do you think is using the most power at this very moment?